Okay, we're very excited today to welcome David Espinosa, telling us about the operational transform by a category theory. Thanks, David.
All right, here we go. So back in 2006, Todd Vilduizan wrote a parody of monads, which is very funny, and you all should check it out. And he mentioned all kinds of stuff, but he forgot distributed systems. So it's my job to add that. So that's what I'm going to do. So we're going to do all of this plus distributed systems. All right. So I worked at Kestrel, which you might know from about 95 to 2000 or so. And when I was there, I worked a bit with Y.V. Srinivas and Duško Pavlović. You might know Duško. Duško's a lot of fun. You should hang with him if you get the chance. And so I learned from them and also from reading lots of papers by Goguen and Messager. And you should read Goggen's career summary for lots of sort of applied category theory. And you should also read Srinivas's thesis, which didn't get enough sort of airtime maybe, but is beyond genius. And that sort of tells you about topology of data structures, which is like super good. And sort of maybe applications of sheaves to pattern matching. Yeah. All right. So prior work in operational transform was invented by Ellis and Gibbs in '89. And I worked from a paper by Sun and Sun in 2009, which is very readable, or sort of kind of enlightening. And I basically, like their paper doesn't mention category theory, and so, sort of you see anything and you're like, well, either this is a totally new thing or it relates to stuff I already know. So I had to accept one of the two alternatives, and I decided to go with this must relate to what I know. So I kind of reverse engineered the theory from their paper. Okay. And operational transform has applications in these areas. It's the theory of at least some version of collaborative editing. It's the theory of version control. It can be used for virtual worlds for multiplayer games. Everybody says eventual consistency. I think a better phrase is functional consistency, because as soon as two nodes see the same exact set of updates, they calculate the same state. So state's pure function of what they see. So the network delivers the updates sort of eventually, but that's not what's relevant to the algorithm. Okay. So the usual or the traditional approach to everybody, all of the participants having the same state, is that you have this replicated state machine and they all see the updates in the exact same order. And so this dates back to Leslie Lamport's famous paper in '77. But you can't do that offline. You can't have guys working offline. They all have to be, it's sort of, everybody has to proceed in exact same order, and if somebody has an update, it has to sort of be ready. So let's see what else. But this is a super important algorithm, and y'all should know it and read about it and kind of understand like different algorithms for total order broadcast. And it's covered in many distributed systems books, and you could make your own algorithm. Maybe you think about it and you make your own if you want. There's another one called causal broadcast, which is the one that OT essentially uses. And that says that updates are applied in causal order. And what that means is that causal order comes from two places. One is if I'm sitting here and I make one edit, and then I make another edit, that's very reasonable at one site. Another place the causal order comes from is if you make an edit and you tell me about it, then all of my subsequent edits are going to be after yours. Okay, so that's what's done. And for causal broadcast, you basically use vector clocks, and we'll essentially see that. Okay, and this is nice because this can be done non-blocking, so people can work offline for like arbitrarily long, and then sync up, and it all happens. So the whole motivation and goal for operational transform is to be able to use causal broadcast instead of total order broadcast. That's sort of the distributed systems maybe view of it. Is OT a good idea? Well, it's offline and it's peer-to-peer. Google uses a central server, but you don't need to. The OT algorithm, and you'll see, works with arbitrary syncing. Like any two people can sync up anytime. And the downside is that you have to sort of say how everything commutes with everything else. And that's sort of n squared work if you have n squared operations. So it's a bunch of thinking in code. Yeah.
So I understand. So Google Docs uses operational transform to manage.
I don't know if they still do, but at least traditionally they did.
Okay. But I also noticed it's very annoying. Sometimes I'm working in Google Doc and the network drops and then I can't edit because I'm offline.
Mhm.
How does that match up?
You can edit locally.
It blocks me from editing locally too.
It shouldn't.
Okay, so the algorithm should support this.
Yes, it should support like arbitrary local editing.
Okay.
Yeah. And so an alternative to this is some kind of real-time protocol where you have a time window, and if people's updates show up outside the window, then they're discarded. And I think this is traditional for multiplayer games. Right? If you're like, I shot you, and then they're like, no, you didn't. Sorry, you were late. So also like Google Spanner database works with very tight clock synchronization. And sort of there's a window of uncertainty about who was first. And if you're outside that window, forget about it. So that's an alternative. But that's sort of, how would you say it, pseudo real time. Or let's say real time. Okay, so it can't do the like crazy offline stuff. Okay, that's an outline. So I'm going to kind of give you the fast summary, and then we're going to talk about time and state and a functor from time to state. I'll show you code. We'll talk about related ideas, which is where things get fun. We'll talk about a topological point of view, and we'll have some comments about kind of building the state category. Okay, so this is fast because I have a lot of slides, so you should definitely interrupt me. And yeah, that's how it's going to go. If I gave it at my normal boring pace, we would get through like I don't know, a third of it. Okay, so the next two slides are examples that are the essence of the whole thing. And so we should work that you understand these examples, because if you have this, you basically have the whole thing. So let's imagine, what are we going to do? On the left, we have the category of subsets of, let's say, the alphabet under containment. Okay, so that's a lattice, because you have intersection and union. And it's a partial order. And on the right, we have the monoid of natural numbers. So there's just a single object, and here we go. And size, so size of A contained in B is the size of B minus A, okay, which is the same as size of B minus size of A. And so that's a functor from the left category to the right category, okay? And so this is sort of one of our key examples, okay? And here, right, this functor has a nice property. On the left, we have a lattice, and we want to talk about how the lattice structure sort of interacts, or how it's used in the functor. And so we have the property here at the top. This might be a little more recognizable to you if it looks funny. It says that the 1 on the upper left is just equal to the 1 on the lower right, and the 2 on the upper right is equal to the 2 on the lower left. If you rewrite that, whatever that equality, it might look like the union, the size of the union is the size of the A plus the size of B minus the size of the intersection, which should, recognize that.
So this
Okay.
minus here is a set minus?
That is a set minus, but we don't care because we have containment everywhere, so, okay. Okay, so let's do another example. We'll keep the left category the same, and we'll change up the right category. So instead of a monoid, let's do a total order. Let's do total order of natural numbers under less than or equal to. And size is, so we'll have a different size functor. Size of A contained in B is size of A is less than or equal to size of B. Okay? And that's also a functor. No problem. And we have this. Okay? And so now let's, let me see. What's the deal? Yeah, close enough. Okay, so this also interacts nicely with intersection and union. The size of the union is as we said, size of A plus size of B minus size of intersection. And what that means is that if you told me, the top two arrows here, I can tell you what the bottom two arrows are, if we start with A and B and intersection and union on the left. Okay? So, and the way that you're going to calculate the 4 at the bottom, can you tell me how to calculate the 4 at the bottom? 3 plus 2 minus 1. Okay? So exciting. Okay? And I'm going to back up to like this example. So again, if I have intersection and union, you know how to label these arrows at the bottom. Okay? You copy the 2 across, copy the 1 across, you're done. Okay? So this is important and relevant. Okay. Way to go. Okay, now we're going to talk about time. So this whole talk is about one functor. It's a functor from time to state. Okay, a whole talk, one functor. Okay, can't be that hard. Okay, and the time category is going to be a lattice. Okay, kind of like we were just seeing. And the state category is going to be a co-commutative category, which you don't hear about a lot. Okay, and that's why, in a sense, why the talk is interesting, because it's about something you don't hear about a lot. Okay, so we're going to build a time category. We're going to build time from events. Okay, and so this goes back to Leslie Lamport, 1977. Leslie said that events are a partial order. So here we have 3 events, A, B, C. A happens before B, and C is independent. And we could say C is unrelated or concurrent or in parallel or independent or whatever. Just language. All mean the same thing. Okay? And what happens next? How could this happen? A way this could happen is maybe we have 2 processes, P and Q, and A and B are editing events in P, and C is in Q. Okay? So typically in the asynchronous distributed systems model, events in different processes are concurrent. Okay? And that's like special relativity, and Leslie knew about that very well in his paper. Yeah.
So this is, for illustration, a picture with like absolute time arrows. So, or do I just? So this starts with P and Q unrelated, and that's the world I live in, and that's asynchronous distributed systems world. Sometimes you see people reading a time axis from left to right. I don't like that world. Okay, and so that's a sort of religious war about whether you think there should be a global time in your distributed system or you don't think so. And so conditions like sequential consistency is a world where you don't have a global time. But if you've heard about linearizability, that assumes a global time. I don't like it. Okay, we can talk later. So another way you could get that same order is if maybe A was sending a message and B was receiving that message, and A happened in one process and B happened in another. This would also be A happens before B and C is independent. Okay, just some examples. But we don't care how it happens. We only care about the partial order because we're mathematicians. Okay, so from events we can make times. Times are downward closed sets of events. Downward closed means that if B is in the set, A happens before B, A has to be in the set as well. That's downward closed. Why should sets of events that have happened be downward closed? Well, if B has happened, A was before B, A must have happened as well. Okay, so it fits the intuition. Okay, there's sets of times are sets of events that have happened. So examples, like, I don't know, AB is the time where A and B have happened, but C hasn't happened yet. Okay? You can't have the set B by itself because if B has happened, A has happened as well. So B by itself is not a valid time, but AB is a valid time. Okay, this is basically formalized by Friedman Modern in 1988. I think everybody knew it probably 10 years before that easily, but nobody talked about it. It's the same concept as vector clocks. Vector clocks, you count how many events have happened at each of your processes. And so that's essentially downward closed. If you say that 8 events have happened at process P, that means like event 8 has happened and everything before it. Okay? Stuff like that.
So these times and vector clocks, same concept, isomorphic, okay, exactly same. We're going to work in this talk with downward closed sets, okay? But if you wanted to represent them using vector clocks, you're perfectly welcome. It's the same thing. Okay, what else? Downward closed sets are closed under union and intersection. The mountain is a picture of a downward closed set. Take the union of two, you can see it's still downward closed. Everything, pick a point, everything below it's in it. Same with intersection. So the downward closed sets of events form a lattice. Okay, so we'll get a lattice. And that's going to be our times. That's going to be the category that is our domain category for our functor. If you want to visualize this as a piece of a hypercube, you could. You would get the full hypercube if you had like a bunch of completely concurrent events, at which point there's no like happens before, everything is concurrent, and so every set is downward closed, right? So like BC would be downward closed, you get the full hypercube. So, but in our example, you can see that as soon as like A happens before B, then BC is no longer downward closed, you just get a part of your hypercube. The reason I want you to, or I think it's nice to think of it, is it gives you a geometric model. Unfortunately, it's kind of in n-dimensional space if you have n participants, which like doesn't necessarily help you very much because we suck at n space, but okay. But why not, right? Okay, so that's it for time. Okay, so now in theory you understand time completely. One more thing we could mention is that if we have the times, we can recover the events as essentially times that are not unions, or under the lattice structure that are not unions of other times. So I'm not going to go into that, but this is sort of well known in lattice theory that you can bounce back and forth between sort of partial orders and lattices and distributive lattices. Okay, so you could get the events back. Okay. They're the non-trivial times, where trivial means it's the union of two others. Okay, so now we want to work on the state category. So we want to capture this idea that if we have the top two arrows, we can calculate the bottom two. So we're going to have additional structure sort of on our states and state transitions. So we start with a category of states and state transitions. And we want to add additional structure, and we want to add this after operator. And so this is from operational transform. That's where this is the transform part. So after sort of transforms F to be after G. Okay, so this is sort of formalizing. It's reducing doing F and G in parallel to sort of doing F and then G after F, or doing G and then F after G. And so this square is supposed to commute. So after has to make this commute. So it's not supposed to matter which way you go. So it kind of produces this arrow down the middle, which is like either the left path or the right path, they're equal. And the arrow down the middle is sort of F and G in parallel. Okay, so sort of reducing parallel to sequential because we only know how to do sequential. Okay, and you can think of this as kind of a three-way merge on your objects. Like if you're in a source control system, you're kind of used to three-way merge. Like if the objects were A, B, C, this is the three-way merge of them at the bottom. Okay. So where's this from? So I'm calling it a co-commutative category. I picked co in a second because it looks like a co-limit. It's the thing at the bottom, and the thing at the bottom is always co. It's implicit in Gabriel and Zisman's work on categories of fractions. If you look in the paper, you won't see the definition explicitly, but you'll see it implicitly. And they wanted to basically say that, that as long as numerators commute with denominators, then you can make nice, pretty fractions. Otherwise, you get these funny alternating chains of arrows pointing either way. And, but look up category of fractions, you'll see. And they borrowed it from ring theory. They just took a construction in ring theory, ring localization, and moved it straight over to category theory. Okay, so I'm kind of attributing it to them.
I just have a question really quick with this. I may be missing something, but is there like an extra constraint in addition to just like the existence of like a push out of F and G?
Yeah, there's
that's
more.
on this?
There's more
Okay.
coming. Yeah.
Yeah.
Yeah. Okay. So it's called co-commutative because this would be commutative if you had a before operator that does what you have above. Okay. All right. Additional. Let's have examples. So for this monoid of natural numbers under addition, we said we would just copy across. And this just, the commutativity of this says that a plus b is equal to b plus a, solid. So that's, but we're choosing a definition of after. Okay, it's structure. Okay. Okay, what else? For the total order one, we saw we'll choose a plus b minus x, and that's guaranteed to be above b and above a. Okay, assuming that x is below a and below b. Okay, very nice. And neither of these was a push out. Like if this was a push out, maybe this would be 3 and 4. And for our structure, it's 4 and 3. If this was that diagram with 3 and 4 has a push out, what is it? What's the least thing that you can put?
Do you not mean it has a push out in the order? Surely not in the monoid.
I went back to the monoid, push out in the monoid. If it's 3 and 4 at the top, what would you put it, what's the least thing you could put at the bottom to make it commute?
There's only one object.
Yeah, but I don't care about that. What are you going to put as the arrows?
Okay. Make it sum to 4, I guess.
Yeah, 0, 1.
Yeah, 0,
0,
1,
and
0,
1
1.
of the other.
0, 1, right?
Yeah.
Yeah, 0, 1. Okay? All right. I mean, you can tell me later if I made a mistake, but 0, 1 is what I'm thinking. Okay? And this one, I don't know, what the crap. Say 2, 3, and 4. This one, push out, what are you going to put at the bottom? Here, the max, right?
Sorry, the max. Sorry,
The max, so 4. You put 4 at the bottom, right?
That is above.
Yeah.
Yeah.
Yeah, so you put 4, right? Okay? But we're not putting 4. We're putting 5. 2, 3, 4. We put 5. Or what did I say? 2, 3, 4. We put 3 plus 4 is 7 minus 2 is 5. We don't put 4. We put 5. Okay. You see, so it's not the push out. Okay. I mean, you could use the push out. Both of these categories have push outs. That would be a different choice of structure. Okay? And that wouldn't result in the functor that we wanted, the pretty counting functor. You'd get a different functor. Okay? Might be interesting. Okay, very good. Let's move on. Yeah, certainly for the max one, for this one max, people be editing on both sides, and you'd join and you'd just get the max. Okay. Whereas here we're going to count, and so it depends on where they split. We would look back, right? Source control, right? We'd look back. Where did you split? You incremented your thing by 3. Well, okay. If this was 2, 3, 4, you incremented by 1. This one incremented by 2. Then we know that since the split, we had 3 increments. You see, working like source control, whereas the max won't count like that. Okay? So you start to see the OT magic coming. Okay, so you said what else? Okay, so I was telling my buddy Antonio, who's a real topologist, about after, and he goes, well, you wanted to be functorial, right? And I go, oh yes, definitely functorial, no question. So identity after F has to be identity, and F after identity has to be identity. And this has to be strictly functorial for my definitions. If you guys want to, make the weak version, you can. I wash my hands of this. Beyond my pay grade. So you compose G and H, you push it after F, and that has to be exactly equal on the nose to if you took G after F and you took H after F after G, then and you compose these two, you should get exactly the same thing. Okay, so it's strictly functorial. Okay, and also on the other end of things, if you took F and you pushed it after G and then you pushed that after H, you should get exactly this. The same as taking F after the composite. Okay, so that has to hold. And we could check that for our 2 examples of the total order and of the monoid that and our choices of after, we could check that this will hold. Okay, and it does. And it'd be good to check it. Okay, there's a thing called the cube law, which is going to play a bit of role in this. And what that says that if you take this f and you push it kind of around the square to the left, and you push it around the square to the right, you should get the same thing. Okay? And this is in operational transform in the literature. I think this is called T2. And when they first did OT, they didn't require it of the after operator. And they figured it out when they like really did the correctness proof, and they were like, hey, we need this to get it to work. And, you know, or basically. And so it holds automatically in a co-commutative category because of functoriality and because the square commutes. Going around the left and going around the right is the same as going after the arrow in the middle, which we talked about before. Okay, so it holds automatically in here. And so that's kind of interesting because it means that when we construct these co-commutative categories, that we're going to need to make sure we use the cube law, kind of.
Do you know whether it's equivalent to functoriality? Is it equivalent to functoriality?
In the case where they were working in, they didn't start with a whole category of operators. They sort of just started with a collection of operators, and you would make sequences of them. And so after didn't operate on sequences of operators, it only operated on one at a time. So we'll see that more later. Okay. Now, the functor from the lattice to the co-commutative category has to obey essentially this property. And this looks, you're like, oh my God, what a bunch of symbols. But this just says that if this is the square over in time produced with intersection and union, and you apply f to it, you should get, since that everything commutes in time, it's partial order, everything commutes, and you apply f, if f's going to be a functor, then of course you'll get a commutative square. And in particular, you should be able to calculate the value of f at the bottom by using after from the value of f at the top. So this is essentially saying that, in a sense, f commutes with after. It's not quite right, but you can sort of see. Okay? Is that sort of clear? You take that, you calculated f on the top, you calculate it there, and you take this one after that one, and that has to be exactly what your functor commutes. Or sorry, functor produces on A contained in the union, on the lower part. Okay, so this is sort of the property. So obviously we have a functor, it's from a lattice to co-commutative category. We want to know how the lattice structure interacts essentially, or is transformed into the co-commutative structure, you know, in the codomain, right? I mean, there's no point in having structure if it sort of doesn't interact with a functor. This is how it interacts with a functor. Okay, so this is like, I'm describing, in the whole talk, I'm describing a pattern, and this is the, you know, one of the pieces, the essential piece of the pattern. Okay? All right. Then for OT specifically, not particularly part of the pattern, we need a user model. And the user model isn't totally, OT is usually done with a monoid. I'm generalizing up to a category. That meant the user model had to be a little more complicated. The user model is essentially producing a state transition for every event. Okay? And the tricky part of this is that sort of knowing what state to start from. Okay? And the way that I formalize this is like, we have a function u, you give it an event, and it produces a state transition, but you also have to tell it where should it start. So u has to be capable of producing state transitions starting anywhere you say. So it's sort of like, if I show you a document and I tell you it's your turn to make an event, then you'll be like, oh, well, from that state, I'm going to insert like the letter Q over here, or I'm going to go delete this X over there. And if I give you like a different document or something, different initial state, then you'll say, oh, well, with this document, I'm going to like, scratch out that B or insert this something else elsewhere. Okay, so this is abstracting the user model. So it's supposed to produce a transition out of F. Like, okay, what do you want to do now? Okay, and so this is used for when we do OT. Okay, and the property that that F is going to have, that our functor F is going to have, is when it's going from the time immediately before E to the time immediately after E, it's going to do the U transition. Okay, so it's going to do the transition, whatever that U creates given E and given the state F of LT of E, which is the time just before E. Okay, so in other words, what we're doing for OT, we'll see in the next slide, we're sort of giving a recipe to calculate this functor. Okay, and we have a recursion and a base case. The recursion is the after relation that I showed you a minute ago, and this is the base case. Okay, and so we'll see in one sec. And what's going on here essentially is that there's pretty much one natural transformation in this talk. There's a natural transformation from the LT functor to the LE functor. And I didn't call them out, but you give me an event, LT produces the time strictly before E, and LE produces the time less than or equal to E. So these are like just before E and just after. Okay, and LT is contained in LE by containment of times. Okay, that's a natural transformation from LT to LE. And if we take that and we whisker it with F, that's essentially U. And U is the thing that sort of roughly takes us from events to states. Go ahead.
You haven't said anything about the category of events.
It's partial order. That's all.
But can you get a co-commutative category structure out of any lattice? It seems like you can.
Yes, you can.
So and then
yes.
It's just a functor of co-commutative categories, right? So
Yeah, but we want that structure on the state lattice, not on times. We don't. Times just a lattice. That's it. All of the co-commutative structure is here on state.
Is there a canonical one if you have an appropriately structured lattice, which is essentially?
Yeah, if you have pushouts, you can use that. And if you have a terminal object, you can use that, but it's really boring because all of your edits immediately destroy your document. You're like, you want to merge? Okay, bang, we just delete everyone, we're done, roughly.
But so push out is always a co-commutative structure.
Yeah, pushout would do it, yeah. And I think we'll see cases where you really do want to use the pushout for some examples. Okay, so that's how we're going to use U.
So
Yeah.
your LT and LE stand for less than or equal to?
Yes.
Okay.
Yes. Okay, so here's sort of OT as a proposition. I haven't proved this, so I should say conjecture, but I think it beats conjecture. So given a partial order of events, co-commutative category of states, a function U is described, there exists unique functor F from time to state that has both my properties. Okay, so this is my claim. And let's see. So existence we're going to see in some code. Yeah, if uniqueness doesn't hold, I'm interested to know about it. I won't. It'll be interesting, but I won't die. I conjecture it's unique. Okay. Let's do some code. This will be in Python. We'll make two functions, F for the object part and the arrow part. And I'm going to kind of go through an example. I'm just sort of flashing this up so people can look at it in detail later.
Okay.
Look, it's a monoid. It has after. And it has, yeah. Okay. And it has a user thing. And here's the total order. This is just the example we had before. And here's the exciting slide. And this is OT in 10 lines. Okay. And the interesting thing we're going to see is this recursive call in red. We're going to kind of see how this works. If it wasn't for this recursive call, this is just one loop and we're done. The recursive call makes it interesting. So what does it do? It takes, CC is just the state structure. It doesn't matter. S and T are two times, two downward closed sets of events. Okay. And it basically adds E, and it picks a nice E that it likes, and it does some computation, and then it adds E to S until S gets up to T. It doesn't change T. Okay, so it just raises S up until T. And so it's sort of gradually building an arrow, we'll see, from S to T. Okay? And the way it does it is, like, if we start with this state, I called it f of 0 for like f of the initial time. But we're looking at what's going on in the state category. Okay? And so it decides it should do A. A is produced by the user action and starting at f0. And so we're going to work with that, those A, B, and C that we saw before. A happens before B, C is independent. And so we pick A, we look where it is, and we recursively compute the red arrow, and then we move the A action that you gave us to be starting after that red arrow. And that's our first transition. Okay? And then we do the same thing. We maybe happen to pick B. You can pick any one that's sort of enabled in your current S state. Okay, enabled means that all of its prerequisites have been done. Okay, like if I'm sitting here and what is it? If you send me action B but I haven't received A, I'm just going to hold on to B. Okay, this is typical in distributed systems. I'll hold on to B and then until somebody sends me A later, and then I can do A and then I can do B. Okay, so B wouldn't be enabled until we've done A. Okay, so what's the story? C is enabled, so C starts at F0, but we're not at F0. Okay, we're already at FA. We've already done A. Okay, so if we want to do C, we have to move it to FA. Okay, so we recursively compute this arrow, which happens to be the same as our first arrow, and just happens to be, and then we move this. We move the C transition after that, and we can put it here and do it. Okay, that's how the code works. Okay, and then maybe somebody sends us B. B initially happens after A, so maybe it happens at FA, but we don't want it to. We don't have FA. We have FAC. We recursively compute this, which happens to be this, and then we can put it after it, and now we've done B. And so the arrow produced by our function was the composite of all three of these, and you'll see in the code. So that's how that function works, that 10-line function. Okay, and what else? There's I think a whole literature in operational transform of how to memoize so that you don't redo too much work. And I'm not an expert in that area. I think that Professor Sun probably wrote the Wikipedia pages for operational transform, and there's like a lot of info there. And I think he's the expert in which algorithm memoizes least and all of that. I don't know about that. Okay. All right. So that, in theory, proves the existence of the functor f if we would show that this is actually a functor and actually has the properties, et cetera, blah, blah, blah. Okay, and in theory, that code could be derived from the two properties that I gave. Okay. Now we're going to start what I think is the entertaining part of the talk, which is relating OT to a bunch of stuff. And so there's going to be, like when I was working on this, I would say, oh my God, I'm working so hard to figure this out. Isn't it just counting? Or isn't it just term rewriting? Or isn't it some existing thing? So this is like, isn't it just counting? And the answer is, yeah, it kind of is. And we saw that. Okay? Next thing is like, well, isn't it just probability? And probability is like counting. And in probability, you know, we can calculate the probability of the union from the probability of the two in the intersection and all of that. But if I give you this setup here, you can't calculate these two just from those two zeros unless you're more creative than me. Okay, that's a joke. Okay, but it turns out probability is actually dual to counting, because counting you're looking at increments from empty, whereas probability you're looking at fractions of a whole. So you sort of start from the top and you work down. So it's dual. So probability would be the same pattern but with a commutative category instead of a co-commutative category. And you can actually calculate these bottom, which way am I going? You can calculate the top two from the bottom two. And the formulas look like that. Okay, and you can verify those. And it comes down to just, what's the deal? Just the usual, again, probability of unions, probability of the two minus the intersection. Okay. It's also sitting in here is the claim that probability is a functor from that lattice over to like the monoid on 0, 1 of real numbers under multiplication. So if you're a category theorist, that's what probability is. And it's exactly an instance of this, this pattern that I'm talking about, okay, but with commutative category here. So this is category, so one of the things you get for free in this talk is categorical version of probability, at least a simple probability. But we only define it, we define it on what's it called? A contained in B. So you start with conditional probability as kind of like your base. Okay, it's fundamental, right? Which is typical for math. You do the relative version. Okay, is OT just Seyfert-Van Kampen theorem, where you're starting with topological space X and its subspaces, and you want to calculate like the fundamental group or fundamental groupoid? And so this is from topology around 1931. Isn't OT just like this? Well, actually, yeah, it is. Okay, and so your after structure here is actually a push out. These are groupoids. This is a push out of groupoids. Push out of groupoids actually isn't that hard. It's pretty entertaining to look at what that is. Okay. If you look at push out of groups, I think it's pretty close. Okay, so yeah, finally a push out. What else? Okay, is OT just conflict-free replicated data types? And let's see, so OT is from '89, but the CRDTs were from 2007 and 2009 or so. And I think you could probably tell by now that these are special cases of OT. I hope I've convinced you. The CRDT people said no, which is why I have this slide, but I say yes. You can look at the two and see whether you believe it. I'm also not super impressed by this work because Gary Kildall, who did the CP/M operating system in the first POPL conference, has a paper on the use of what's it called, semi-lattices in compiler optimization, right? It's the standard, what's it called, data flow analysis, which he invented, first POPL, 1973. And that's just the idea that, you know, you can do a chaotic iteration and you just keep taking unions and you'll converge and, you know, you're all happy. And so, you know, the op-based version of CRDTs is doing that. And so they decided, you know, they talked about in 2007, well, I date that to about 1973. Okay. And then, or no, yeah, that's the semi-lattice one, sorry. The commutative monoid one, I date that to the first caveman who was like, oh, 3 plus 4 is 4 plus 3. You know, you have a bunch of numbers, we don't care. Okay, so OT removes the duplicates when you do counting. So a good example is to see what do you have to do to get your CRDTs to count correctly. Okay, like if people are incrementing counters, right? If you just take max, you're going to be too low. Okay, so OT kind of does the right thing in the framework, it doesn't do it in the data type. So it's good to do it in the framework, like, because then it's done once and for all in your OT code. And so when we wanted to do counting, we just instantiated with either of those two examples that we saw. We didn't have to put any lattices in our data type, which I think is what you had to do in CRDTs to get this to work. Okay, another example. Is OT just term rewriting? Term rewriting, you start with one-step rewrites, and you sort of get multi-step rewrites and convergence of multi-step, whatever, what's confluence of multi-step rewrites. And indeed, that is a co-commutative category. But these are relations, and so you don't actually care about your paths. So it's a relatively simple case of a co-commutative category. If you want to do labeled term rewriting, where you care about not just did you get to this point, did you find a common term, but how did you get there, and you want to track the paths along which you did your rewrites, okay, then you could potentially use OT. And typically in term rewriting, you just work with diamonds, whereas sort of OT sort of maintains a bit more of the time structure, where you've got a whole bunch of different people rewriting, and they're starting from different places, and it's like, does it essentially, is it confluent? And the answer is yes. You use the OT algorithm, and that creates kind of the final state. Okay, so if you were to work that out in term rewriting, where people were kind of rewriting in different ways, then you would wind up at the OT algorithm. Okay, so is OT term right? Well, kind of, yes. Okay, what else? Okay, is OT just topological sort? Because we saw in causal broadcast, essentially, that if you have operators, you're maintaining what happened before what. If you tell me about an edit, then all of my subsequent edits have to happen after yours. So isn't this really just topological sort? Aren't we done? And in the time part of it, we are kind of done. But OT is also talking about transforming operations, which pure topological sort doesn't talk about. And also, if we had our usual A, B, and C, ACB is a topological sort of that. That's fine. But we can't factor OT through this. It's not enough just for me to tell you, hey, ACB, do it in that order. If we didn't need to track dependencies exactly, then we could just go, oh, I just do ACB? Okay, ACB, I'm done. But as we saw, we have to know that B essentially depends on A but not on C. Okay, so we have to pay attention to those dependencies. It's not enough just to know like any old topological sort and then be done. So OT takes account of these dependencies, but it doesn't factor through topological sort. Would be nice if it did. I call this topological sort. Here's a version of the same sort of the proposition that I gave earlier. This one, instead of a co-commutative category, I'm taking a monoid. But it's not a commutative monoid necessarily. And this one is actually a little more special because M is a monoid, but it's a little more general because it doesn't have to be a commutative monoid. So this sort of proposition is independent of the other one. Neither is an instance of the other, but they're closely related. And what this says is that if you can make it so that whenever you have, you pick your U operation from E to M, and whenever you have two events A and B, okay, that are concurrent in E, then they should commute over, their images under U should commute in M. So if you can get the conditions on the top, arrange everything, then I claim there exists unique functor F obeying these things. The quality of those two is essentially that we're using the appropriate after for M being a monoid, which is just that you copy across. Okay, and then, yeah. So this is sort of a variant of the proposition I saw earlier, that we saw earlier. Okay, so this would be, and I thought it's nice, so I put it up. Here's an example. M could be pairs of strings, and A and B are sent over to strings on the left, and C is sent over on the right, so that A and B don't necessarily have to commute, but A and C have to commute. These are strings in append, and B and C have to commute. And so if you make the unique functor according to that recipe, you'll get something like this, that you hand it empty is contained in ABC, and it will put AB on the left, not BA, and it'll put C on the right. Okay. All right. Okay, is OT just a commutative diagram? So the answer to this is yes. So we think about time as being the shape of the diagram, and then we have U as sort of labeling the individual transitions, and we label with U and after. And then we'd like to show that the diagram commutes. The advantages of viewing it this way is that we don't have to say co-commutative category, and we can just label sort of one edge at a time and use after just defined on single operations. So this is actually more traditional in the OT literature. Okay, and let's work this way a little bit. So when we're labeling our kind of graph of times, we would like to know that we're labeling it nicely. And so when we're labeling the edge at the bottom, did we label it by moving F across sort of over on the right, or did we label it by moving F over on the left? And so you can kind of see that we're going to need this cube law to make sure that we've labeled, if we're labeling using after. So F, G, and H are all created by U, but then we have to push them to the other times using after. And there can be some choices about how we label things. And so all of our choices have to agree. So that's where we might need this cube law. Okay? So this is sort of in traditional OT maybe where the cube law is getting used. And then the next thing, so now let's imagine that we have our whole time graph labeled. It's like now we have this hypercube. How do we know this thing commutes? Okay? How do you know that a diagram commutes if it's a fancy diagram? Does anybody have an answer to that offhand? Super crazy diagram like a hypercube. How would you, usually we do diagram chases by hand. We're like blah, 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 push everything by hand, blah, blah, blah. I know it's hard to guess what I'm thinking, but there's a particular, let me know in 2 slides. So here's a proof of pasting lemma, right? You start with this. That's equal to this the composition along this path, because the left square commutes, and it's equal to the composition along there because the right square commutes. Look at this. Is this reminding you of anything? There's a word. No? This path is getting transformed into that path. What's that called? Homotopy, right? Homotopy. Okay, there's the word. Okay, so commutativity theorem. So this is old school. The new school version is you just say, oh, well, from our equalities, we make a 2-category, you compose 2 arrows, you're done, everyone's happy. That's the new school version. The old school version is you say that if all parallel paths are homotopic and all faces commute, then the diagram commutes. Okay, and so that's a global condition on the shape, right? Doesn't involve the labeling, it's just the shape, just the whatever the homotopy of paths. And then the faces commuting, that's a local condition on the labels, right? And you get a global condition on the diagram. And sort of the insight here is that you need to have faces, right? You have to start with not just a diagram, not just the edges and the vertices, but you have to have a notion of what's a face. So you have to move up a dimension. Okay, right, that's okay, very nice. It would be nice if that was in like an elementary category theory book, in my opinion. Okay. So for a 16-dimensional hypercube, there's 16 factorial paths. You'd have to check 10 to the 13th paths. But this is very nice because if you have that theorem and you believe that all of your paths are homotopic, then you only have to check 1,000,000 faces. Improvement of factor of 10 to the 7th in efficiency. Who says that math isn't good for something? Okay. So all the topologists will tell you that, the whole purpose of homotopy is classifying topological spaces, but since we're category theorists, we say, no, the real purpose of all of that work you've been doing is to show that diagrams commute. Okay, all right. So which brings us to this, is Otija-Stokes theorem. Before we were back at 1931, now we're back at 1850. And so if we have these two paths and we want to show that you integrate f across each one and they're equal, well, if you know the curl is 0 in the inside, which means that each of those little squares commutes, that's curl 0, then and you know they're homotopic, then you're good to go. Okay, so is Otija-Stokes theorem? Yes, it is. Okay, 1850. Okay, so for some books on topology and concurrency, there's a couple that are on distributed computing and topology, and you should read them. Okay, and you should also read Robert Grist's book in 2014 on topology, just because it's entertaining. And it's kind of a new kind of math book in a certain sense, because it's almost like popular. It covers lots of stuff, and it's not formal, but it's like rock solid. It's like actual math. So I think it's almost a new style of writing a math book. Okay, all right, and it's a lot of fun applications and things. Okay, I am going to, I think we have time to do this sort of. So what's funny about this talk so far is I haven't really done any programming language stuff, and I tend to work more in programming languages. So, I promised you programming languages at the beginning. So if we start with like a collection of basic operations, and this is how OT usually goes, and we define after for each pair of basic ones, then we'd like to build a co-commutative category, right? So this is like, I could have waved hands and said, oh, it's trivial, you just use sequences of operations. We're going to find out it's not as trivial as you thought it was, or as I thought it was. Okay?
David, just to find out how non-trivial this is, we've got something like 0 minutes left. So.
We started late.
Yeah. Oh, you got a couple, we'll see.
Okay, yeah, it'll be fast. And so we want to build this co-commutative category. So let's imagine, I don't know, for syntax of operations, maybe I have operations like append an A or do a reverse and whatever. And, I love categorical logic, so I didn't, okay, fine. And so paths in this are the syntax of our set of operations, right? Very nice. And if we take those paths to be our co-commutative category, we do composition just by appending paths. It's great. We can do after. It's functorial. Like you can just push your operations. You do this, and then like this path, you make after. Now on paths, it's no problem, because you had it just on individual ones. You extend the paths. And then you ask, does this diagram commute? Right? So this is like 2 plus and 1 plus and 1 plus and 2 plus. Does this commute? Seems like it, right? Seems like it. Everybody agree? Commutes, we're solid, we're good, rock and roll? I wouldn't be asking you, would I?
You mean like
What?
An actual data type?
What category are we in? Somebody shows you a diagram, you should ask, what category are we in? We're in the category of paths in the previous slide.
Yeah.
Does this commute? No, doesn't commute anymore, right? What category are we in? In set, of course it commutes. In that category of paths through a graph, no, these are different paths. This says go 2 plus and then 1 plus, 1 plus and 2 plus. This doesn't commute. So if this was our nice definition of after, right, whatever, you know, we defined after, we thought we were done. We're not done. This doesn't commute. Crap. Okay, so what do we do? What we're going to do is we're going to quotient the paths to make after commute. So what we're going to do is we're going to take every pair of operations that we have, and we're going to compute f after g and g after f, and those are just singleton operations, right? And then we're going to look at this, and we're going to essentially quotient by this to force those to commute. So we're going to make a category where after works. We're going to force it to work. If it doesn't work, we'll force it to work. And that's the category that we work in. Okay? All right. Is after well defined? Well, so when you quotient, now we want after to be a function, but now we're quotienting, we have to make sure it works on our equivalence classes. We have to lift it to the equivalence classes, right? It was nice on the paths, but now put it on the equivalence classes. In order to get that to work, we need the cube law. So do you remember we weren't depending on the cube law? Cube law comes for free in a co-commutative category. So if it comes, you can't get something for nothing. Surely we have to use it somewhere when we build this co-commutative category of operations. Here's where we're going to need it. Okay, we're going to need it to prove that after is well defined. Okay, and we have to show that after is well defined on the left and well defined on the right. Okay, blah blah blah. So we saw, we saw that if we didn't use co-commutative categories, we just did labeling with like diagrams, then we needed the cube law to label consistently. But if we build a co-commutative category, then we need to use the cube law to build the co-commutative category that we want to work in. So we saw some uses of it. And it's interesting how to understand this cube law intuitively. A possible interpretation of it is that it's showing or claiming that nothing non-trivial is happening inside the cube. So it's sort of potentially reducing this from like some problem with non-trivial homotopy in 3 dimensions to something that's trivial in 3 dimensions. So potentially reducing the dimension of this thing from n down to 2. But that's in the level of wild conjecture. Because we started with an n-dimensional problem. But the thing is that everything we've done has just been in 2. Okay? Okay, good. So here's the summary. You can remember the 2 examples that we saw before. Those are the 2 examples. We're solid. I'm done. Okay? Right. Okay. Questions? Yeah. I know it's a lot. I know it's a lot and it's fast and all that, but you didn't think I could do 70 slides in an hour.
Absolutely not. Do you have a favorite implementation of operational transforms, preferably open source?
No. The one on my slide in 10 lines. Sorry, I don't. I'm a theorist. If you, right, from your point of view, I'm an applied guy. From the software engineering point of view, I'm a theorist. I fall through the crack in the middle.
Well, we write software. You're also an applied. You're also a theorist from our point of view.
Okay. All right.
Have you, is this talk the like publication on all of this? Is there anywhere else you've written about this or anything?
Nope.
Okay.
I have I put another talk on YouTube recently because I didn't know if you guys were going to have me here, but it's essentially same as this, mostly same. Yes, nobody is paying me to write this all down and formally verify it in Lean or whatever, you know. So no, this is it. And if anybody feels like you know, formally verifying it or extending it or proving anything, they're more than welcome.
I want to make it do cool stuff.
Sure, make it do cool stuff. Yeah, absolutely. Yeah.
Are there any like I don't know, particular like wild examples that pop up from that like free co-commutative category on an after operation that you presented at the end there with that? If like in other circumstances, I don't know. I
Like-
just found that particularly striking. Like that construction seems like it would make interesting things happen, but I would reason out in the brain.
I mean, you should be able to think of it all as, you know, sequences of operations, something like that. But something that's wildly different, no, I don't have anything.
All right, let's thank our speaker again.
Okay. All right, thanks, guys.
Okay.